Welcome to this explainer. Right, let's jump straight in. Today, we're exploring an invisible force that literally shapes our entire reality. I'm talking about a phenomenon dictating how the tiniest microscopic molecules behave, all the way up to the absolute grandest, most violent storms in our atmosphere. We're going to decode the electric field. So let's kick things off with a bit of a brain teaser. Think about your day-to-day life. What do a sock sticking to your sweater in the laundry, a massive lightning strike lighting up the night sky, and the very DNA inside your cells have in common? I know, it sounds like a trick question, but the answer is pretty profound. They are all governed by the exact same invisible force. That very same static electricity that mildly annoys you doing the laundry? It's driven by the identical physical laws that literally hold our biological blueprints intact. Pretty wild, right? To grasp how this works, we're going to break this down step by step. We've got 1. The invisible force field. 2. Mapping the unseen. 3. When fields collide. 4. Electric cousin. And finally, 5. The spark of life. All right, section 1, invisible force field, defining the E field. So we need to define this abstract concept that permeates the seemingly empty space around us. Basically, an electric field is the region surrounding electric charge where that charge exerts an electric force on any other test charge you place inside it. Mathematically, scientists represent this as E equals F over Q. Put simply, the electric field is essentially just a measure of force per unit of charge. And because it's a force, it's what we call a vector quantity. This means it doesn't just have a magnitude or, a strength. It always has a very specific direction. Now, that direction isn't just random. It follows strict binary rules based on the type of charge creating the field. For positive charges, the field radiates outward. It pushes away from the source. But for negative charges, the exact opposite happens. The field points inward, pulling directly toward the source. Honestly, if you can just remember this basic push and pull outward and inward rule, you've already unlocked the fundamental behavior of how these invisible fields originate and terminate in space. Moving on to section 2, mapping the unseen, visualizing fields. So how do we actually see something invisible? Well, brilliant minds like Michael Faraday had to figure out a way to visualize this stuff. Initially, you might imagine a field as this messy, chaotic jumble of individual force arrows, with each one representing a tiny push or pull. But by standardizing this, those tiny arrows are replaced by smooth, continuous field lines. It basically becomes a map where the lines perfectly trace the direction of the force, literally making the invisible visible. But just like any map, this one has strict rules of the road. First, as we just established, field lines must always begin on positive charges and end on negative charges. Second, the visual density of the lines, like how close together they're drawn, is directly proportional to the field strength. So more lines crammed together simply means a stronger force. And third, and perhaps most importantly, field lines can, logically, never, ever cross. Why? Well, because a field can only have one unique direction at any given point in space. If they crossed, it would imply a single particle is being pushed in two different directions at the exact same time, which is, well, physically impossible. Okay, section 3, when fields collide, the superposition principle. This concept brilliantly illustrates what we call the superposition principle. Think about what happens when multiple charges enter the exact same space. When two identical negative charges share a space, their lines fiercely push apart from each other, which creates this weak, essentially canceled out region right in the middle. But when you have opposite charges, one positive, one negative, the lines powerfully connect. The field flows from positive straight into negative, beautifully amplifying the region between them. Now, I want to slow down just slightly here, because this isn't just a conceptual drawing. It's highly precise math. When scientists calculate the total field for multiple charges, they get exact magnitudes. Take this, for example, 1.26 times 10 to the 5th newtons per coulomb. To put that into perspective, that's 126,000 newtons per coulomb. The big takeaway here is that total electric fields are exact, calculable vector sums. Let's look at how this builds practically. The good news? You don't always need complex calculus to figure this out. By mapping two separate field vectors acting at a right angle, say E1 pointing up and E2 pointing left, we can actually just use basic high school geometry. By using the Pythagorean theorem to draw a right triangle, the hypotenuse perfectly gives us that total combined electric field magnitude and direction. It's like a giant puzzle, but the pieces fit together mathematically. All right, section 4, electric cousin, parallels with gravity. To really ground this concept, we need to look at the fascinating parallel between electric fields and a force you experience literally every single second: gravity. Notice how Newton's law relies on mass, while Coulomb's law for electric fields relies on electric charge. Both are central, conservative forces that obey an inverse square law, meaning their strength drops off exponentially over distance. But what's the main difference? Well, gravity only ever attracts. Electric fields, however, can both attract and repel. It's a subtle but massive difference in how the universe operates.
And finally, Section 5, the spark of life, biology and physics.
We so often think of biology and physics as these completely separate domains, right? But classical electrostatics plays a massively important role in molecular biology. Large, life-essential molecules are actually usually electrically charged. In fact, our source notes that it is the electrostatic force that not only holds the molecule together, but gives it structure and strength. That's right, the exact same field we've been calculating acts as the literal architect of your DNA. Which leaves us with this final, truly mind-blowing thought. Every single cell in your body is packed with DNA. And if that DNA is physically bound together and given its structure by the pushes and pulls of positive and negative charges, are we ultimately just incredibly complex, walking, talking electric fields ourselves? It's something to think about. The next time you experience a shock of static electricity, remember, you are interacting with the exact same invisible fabric that makes your own existence absolutely possible. Thanks for joining me on this explainer, and keep questioning the invisible world around you.